So I'd like to make a video this time talking about the approach to designing state machines, including the recommended approach that I'd like you guys to follow for 361. Whenever you start a digital design, it's really important to have a well thought out plan. So you need a form of documenting what it is you want to design. With respect to state machines, there's a couple of well-known different approaches. The approach I would recommend is what's called a state transition diagram, often called a bubble chart. We'll see an example of this later on. We're going to be using Pong Chu's state machine as the example, since it's the implementation I'm asking you to put together. Each state is represented by a circle, and within each circle is a documentation of what the output should be when you are in that state. And the transitions between the states are documented by arcs, and above each arc is documented the value or values of the inputs that caused the state machine to take that transition. When you talk about a state machine, there's really two basic schools of thought. They're taught. One is called a Mealy machine, one is called a Moore machine. You can express the primary difference by the expressions. For a Mealy machine, the outputs Y are a function of the present state and the inputs. Whenever you see a function, you think of a combinational cloud. A Moore machine, the output is strictly the function of the present state. The implementation I'm going to recommend, we'll see, is a further definition of a Moore. So let's look at the first two with the Mealy machine and the Moore machine. In the Mealy machine, you can see that there is a register which is common to all three representations of state machines. It's the register that contains the present state, the input to which the D term is always the next state. The next state is generated by a combinational cloud. The combinational cloud in all of the state machines for the next state is a function of the present state and the inputs. With the Mealy machine, the output is a function of the present state and the inputs. So we have this combinational cloud on the outputs. This is not necessarily wrong, it's just not preferred for a teaching mechanism, in that the timing of the circuit now typically goes flop to flop. But this path, even though the state is coming out of a register, the input is passing right through. And it's a little problematic with respect to doing the timing analysis. We'll see this later on. With a Moore machine, you see the same construct where the state is registered. The difference is the output is a function of the present state. This is not the only way you can implement a Moore, as you'll see in the next example, but it is one that's allowable by the definition, where the output is a function of the present state. What I personally don't really care that much for is now we have gates on the output of our state machine, stealing a little bit of the time that we have to get to our destination. So let me summarize quickly. What is a state machine? A state machine considers, where am I? What are my inputs? Where do I want to go? And what do I want the outputs to be when I get there? Again, what is a state machine? It's considering, where am I? The present state. What are my inputs? Where do I want to go? and what do I want my outputs to be when I get there. So based on my reading and my experience, I've come to a third option that I call a modified more. This is what I expect my students to practice in class. It's like a Moore machine with the exception that the outputs are registered as well as the present state. We'll see in the next couple slides, this makes a very clean way to design your state machine. The diagram looks like this. Both the outputs and the present state are registered. In order to achieve that, out of the combination of clouds, we need to generate the next state and the next output, each of which is a function of the present state and the inputs. So again, the primary difference with a modified more is that now we're insisting that our outputs are also the output of a register, outputs of a flop. When we write the Verilog to implement the state machine, there's always the need of two procedural blocks. I say procedural, I mean the always blocks. The one will be the combinational always, and this is responsible for generating the next state and the next output. The second block, procedural block, is the sequential always, meaning that we're generating flops. Here, the responsibility of this block is to generate the present state and the present output. Now we can see by the code on the right an example of a somewhat nonsensical state machine, but it shows the primary architecture of the Verilog when we're creating a state machine. There's two always blocks, the sequential always block and the combinational always block. The sequential always block is very straightforward and should be the same in all of our designs. The sequential block is always responding to either the clock or the reset. In the event the reset is active, you send your design to the initial state, which is typically 0, and you force all your outputs to be inactive. Once reset goes away, the state machine begins executing, and what happens is we want the value on the next state to be assigned to the state, and the value on the next out to be assigned to the out. The combinational block is strictly involved in generating the next state and the next out. Here, combinational block sensitive to the asterisk, meaning when any input switches, perform the function. Typically, you have a case statement where you're sensitive to the present state. Then, depending on what my inputs are and what my present state is, I then generate the next state and the next out. For terseness, to fit on a single slide, I've used this type of representation. Doesn't necessarily mean you have to use that exact representation. But the goal of presenting this is to show a template for creating state machines while you're in 361 and 460. Our state machine will function as our debouncing circuit. And as we said, our debounce circuit is really a digital filter. And we'll see its responsibility is to filter out any transitions on the input that are less than 20 milliseconds. The algorithm that we're implementing is from Pong Chu, figure 5.9. So although Pong Chu has an implementation, he has the Verilog in the book, I strongly encourage you to write your own code. Learn how to study other people's work to understand what they've done and what your options are. Then be able to create your own work. The description of the debounce state machine is implemented in order to deal with mechanical switches. When a mechanical switch moves, there is a high probability that there will be contact, no contact, contact, no contact, as the metal is sliding across the other piece of metal. What we call this a bounce. For a certain period of time, as the switch is transitioning, the output of the switch is bouncing. If you were assigned this task in industry, most likely what you would do is purchase a handful of the switches that you're required to interface to. Then you would characterize them by taking them to the lab, measuring the duration of the bounce, then ensuring that the circuit you design meets the worst case behavior of your switches. For us, we're just going to accept Pong Chu's assertion that the bouncing will settle in 20 milliseconds or less. So as I stated previously, what we're going to do is we're going to design a digital filter which will filter out transitions less than 20 milliseconds. You can look at this in Pong Chu's representation of 5.8 and see that he had two options. The option referred to as scheme 2 on the bottom is not what we're doing. This option causes the output to switch whenever the input switches. The problem with that is if there's a glitch on the input, your machine would still respond. So what we're implementing, which is seen in the two red circles, is a circuit that will behave such that the input to the state machine must remain stable for at least 20 milliseconds in order for the output to switch, whether we're transitioning to a 1 or to a 0. That is why we call this a digital filter, because even though the input is bouncing up and down, the output stays as a 0 or a 1. So it's as if that bouncing never occurred. In essence, we're filtering those signals out. Now, we've been talking about 20 milliseconds, and we all know that the frequency of the board's oscillator on the board we're using is 100 megahertz, which gives us a 10 nanosecond clock period. So 10 nanoseconds to 20 milliseconds is a long way away, a million times, 2 million. So we need a scheme that would allow us to keep track of quote-unquote real time. We need to know when a specific amount of time has elapsed. The time that Pong Chu chose that I'm going to utilize is 10 milliseconds. Our job is to create a circuit that will let us know when 10 milliseconds has elapsed. That will allow us to incorporate that into our state machine to ensure that we implement a design that guarantees that the signal is stable for at least 20 milliseconds. So the circuit that we need first is this pulse generator. That's behavior will look like what's on the bottom. It'll be active for 1 clock, and it will then be inactive till 10 milliseconds has elapsed, and it'll fire again. So when we do this type of circuit, what we have to do is do the math to figure out how long we have to wait. So since our clock frequency is 100 megahertz, we know the period is 10 nanoseconds. The fundamental question is, how many clocks will there be in the desired period of time? In this case, 10 milliseconds. So when we do the math, 10e minus the 3 divided by 10e minus 9 gives us 1e to the 6. So we see that our counter needs to count 1 million 10 nanosecond pulses to give us a 10 millisecond period. So our counter should run from 0 to 999,999. The circuit then, we need a counter in order to measure what we just were looking at. It needs a comparator to know when we've reached the terminal count. and that it needs a multiplexer to allow us to select either between the clearing of the counter or the incrementing of the counter. Before we begin, we have to consider how many bits do we need in our register. We've just seen that we want to count to 999999. And if you recall from Mr. Allison's class and my class, if we've talked about it, that we all should know 2 to the 10th is 1024. Therefore, 2 to the 10th times 2 to the 10th is 2 to the 20th, which is our 1 million. So since we're counting to a million, essentially, 999999, we therefore can deduce that we need 20 bits in our register in order to hold the value 999999. The circuit we create will look like this. The register in the middle is quote-unquote the counter. It holds the state of the counter. That will range in values from 0 to 999999. The output of the counter is continuously run through a comparator. So the equal sign in the question mark is asking, are they the same? Most of the time, they will not be the same. So our output will pass through a combinational block to increment the state by 1. And the pulse, since it's not matching, will be a 0. So the mux will select the 0 input. So what will happen is on every clock, our counter will continue to increment by 1. But there will come a time, once we've counted to 999999, once we match the comparator, that will generate our 1 clock-wide pulse out, and at the same time will tell our counter to start counting again by loading the zeros. Be careful if you are going to copy Pong Chu. He has a mistake in the way he has implemented this circuitry. So the circuit is adaptable, just to make a general statement. You could generate any pulse train that you would like. You just need to be able to do the math and make sure that your register is large enough to hold the value. You could also have a programmable pulse generator if you wanted, and then you would do that by having the 999999 sourced from a register that you could then choose what your terminal count is, which would then alter the behavior of the circuit to give the pulse train at the frequency that you have designated. Here we find our state transition diagram from Pong Chu. And for myself, I assume that reset puts us into the 0 state. You can see that each of the columns, 0, wait 1, 1, wait 1, 2, wait 1, 3, and then the 1 column. Whenever you're in the left column, the output will be a 0. Whenever you're in the column here, the output is a 1. He has documented that by putting the dB equal to 1. He should have put the dB equal to 0 here. The way the state machine works, we've got over in class, but let's look at it. The documentation has an SW with an tick. This means whenever the switch is 0, we stay here. Now recall, in this state, the output is always a 0. So if the output's a 0, the input's a 0, we're happy. We don't need to do anything. It's only once the switch goes to a 1, we will immediately change states. If by chance there was a glitch and it goes back to 0, we go back to the 0 state. We will stay in this state until the switch remains a 1, and our M tick is still a 0, we stay here. It's only once it's a 1 and we see a tick, we go to the second, and so on. So we're progressing from the first state to the next state, and to the next, and to the next, only on a 10 millisecond tick. If our signal ever goes back switch ever goes back to a 0, we return. Now the same is true here, except here now we're a 1 and we're waiting for the output to go to 0. So we went through this in detail in class. I think this is good enough. You should be able to follow it yourself. If you have a question, bring it to class. Here is Pong Chu's explanation. Let me go ahead and just read it. The slide and push button switches on the prototyping board are mechanical devices. When pressed, the switch may bounce back and forth a few times before settling down. The bounces lead to glitches in the signal, as shown at the top of figure 5.8. The bounces usually settle within 20 milliseconds. The purpose of a debouncing circuit is to filter out the glitches associated with such transitions. The debounced output signals from 2 FSM-based design schemes are shown. The first scheme is discussed in the subsection, and second scheme is left as an exercise. We, of course, want the first. A finite state machine-based design uses a free-running 10 millisecond timer along with the state machine. The timer generates a 1 clock cycle enable tick every 10 milliseconds, and the state machine uses this information to keep track of whether the input value is stabilized. In the first design scheme, the finite state machine ignores the short bounces and changes the value of the debounced output only after the input is stabilized for 20 milliseconds. Then jumping to the bottom, we say since the 10 millisecond timer is free running, the 10 millisecond tick can be asserted at any time. The finite state machine checks the assertion 3 times to ensure that the signal is stabilized for at least 20 milliseconds. This will be an assignment I give you in class to explain the final paragraph here. Here is the block diagram of our state machine. We have the top level, which will have the pulse generation circuit and the state machine itself. The button will come into the state machine, the output of which will be the debounce signal. The counter will generate the 10 millisecond pulse, which will also be an input to our state machine. So lastly, I acknowledge that the source code for this design is contained in Pong Chu's book. It may be tempting to copy his work, but if you do, make sure you acknowledge it in your header. I hope you don't. I hope you take the time to study Pong Chu's implementation in light of the documentation that we've seen. Then form your own opinion and write your own code.